Oh, welcome to Earth Science, everybody. How are we doing? Happy Monday. It's probably Monday when you're doing this. So first, if you didn't do this, stop this video. Go back and do it first. See up here where it says first, try to fill in the reasons. Take some guesses there, and then try these questions. Then come back and watch this video and let's talk about it. Because I think it's going to take that. Like if I just say it all and you write it all, maybe that's not the best. I don't know. Maybe it is. But I think the best way is going to be for you to try to at least get some guesses around this. Because the test can come up with all this, and this is why it's a confusing unit, because you got to deal with the Earth going around the sun, you got to deal with the moon going around the Earth, while all three of these are spinning. Now, the spin of the sun doesn't necessarily have a ton of effect on the things we've studied, but all those other combos do. So let's do it. Why do we have days? Thanks to, let's get a better color than that, Earth's rotation. We spin so that half the planet is facing the sun, half the planet is away from the sun. And, that's how it goes. It's day and night, right? Should be used to that by now. Why do we have years? Our idea of a year is based on how long it takes for the Earth to revolve. So that's Earth's revolution, which, I'm going to be lazy and copy. Oh, that didn't work. Also comes into play here. But also, we need the tilted axis to come into play here. Because what that's going to do, if the Earth were straight up and down, that's actually some interesting questions. Ponder that. What would happen to seasons if the axis were straight up and down? Or what would happen to seasons if we went from a 23.5 degree tilt like that up to a bigger tilt, like 35? What would that do to summer? What would that do to winter? If you really get what summer and winter are, then that should be an interesting question. Why do we get moon phases? This is because of the moon's revolution. And that's a kind of a loaded little statement right there, right? Because then we had to look at how half of the moon is lit as it goes around us, and therefore what we see from Earth is a different portion of that lit half. Like if the moon's over here, you're only going to see the dark part. If the moon's over here, you're only going to see the lit part. Everywhere else, you see some combo of the two. And on that note, there's eclipses, right? I totally left that out of this unit, partially because we ran out of time, but also deliberately because we've got a significant event in the spring, and I think it'd be better just to save eclipses for then and talk about it. It'll be a bit weird to do in the middle of rocks or whatever we're into, but I think it'll be more valuable because you'll be facing eclipses. Sneak preview, they happen because of like the moon's orbit and where it falls in between the Earth and the sun, or where it falls between the Earth and the sun. Don't write anything there because it's not going to be on this test. Why do we have tides? This is a really hard one because this has to do with the moon's gravity, and that's maybe not a perfect answer because it's really the gravity that exists between the Earth and the moon. It doesn't fly away because of gravity in the same way it yanks on us. So maybe the gravity between the Earth and the moon would be the better way to say it. But really those tidal, like the bulge model of tides follows the moon's gravity. So maybe that is a good way to say it. Have I said maybe enough in this video? What else? Earth's rotation. Because if this moon is like yanking on our water right here, the Earth's got to spin all the way around it every day. So it spins through the high, spins through the low, spins through a high, spins through a low, and gets about 2 of each per day. But while that's happening, we've also got to deal with the moon's revolution. Because in different spots, there's different effects. And that's where you really should, like, side note, study your spring tide and your neap tide from the review sheets that we did today on Friday. What's our basis for latitude and longitude? Now, here's, like I said, the day we did this, here's how you irritate an earth science teacher. Get this question wrong because it's so easy to us. It makes so much sense to earth science teachers, but it's kind of an abstract idea for some reason. All it is, your latitude is the altitude of Polaris. That's it. In my seat right here in this classroom, if I point north, there's root 11 over there. I'm parallel with it north. And I point up at our latitude, that angle right there, which is our latitude, is about 44 degrees. I'm pointing at Polaris. The ceiling's in the way. It's daytime, but I'm sure it's right there. That's how they invented latitude. It's not a coincidence. that star that sits directly above our pole, whatever angle you got to look at to see it, boom, there's your latitude. Couldn't be easier. Longitude couldn't be harder, because to do this, you're dealing with being on an Earth that is spinning. Let me grab a little model for you and raise my seat. So you're on an Earth that's spinning. Now, again, latitude is just, if I live here, I look up to see Polaris, which is right above that pole. Longitude, though, has to do with what time it is as we spin underneath the sun. And if you don't know what time it is, because let's say it's some moment in history before there's watches, it's really hard. So early maps were very good north-south and very bad east-west. So the basis for longitude has to do with time and where we are under the sun according to our rotation. Rotation of Earth under the sun. At that speed of 15 degrees per hour. So again, go to the age before there were portable watches. Get offshore in a sailboat and you lose sight of land. You can do your latitude every single night, but you would have to know exactly what time it is. You can do your own solar noon, what time it is on your meridian, what time it is on your line of longitude. You can say, okay, sundial wise, there's solar noon. But unless you know east-west exactly what time it was where you left or how long ago you left, you're toast. You can't really figure it out with numbers. And the invention of like clocks, chronometers that could work out at sea actually like made mapping what it is today. So yeah, as we spin underneath the sun, that is what gives us our longitudes. It's a little trickier to figure out. And along with that, the time zones will go with longitudes. And here's the same arithmetic we've done over and over again. We have 360 degrees of longitude. We have 24 hours. So we didn't like, it used to be that like, okay, solar noon was when I went underneath the sun in my town. Everybody called that noon. The sundial worked. The sun was at its high point. That's noon. Then the sun started going towards the west. It went down. And you couldn't get anywhere else fast enough to have it matter. By the time you left one place, if you left New York City, by the time you made it to Chicago, it would take like weeks or months to get there. So if it was a little bit later there because they're further west, no big deal. Now it's solar noon there. I don't notice that difference because I've been riding in a horse-drawn carriage or something for weeks, right? Once we had transportation that could go fast enough, like trains, we had to say, hey, New York City, we're in Chicago, we're sending a train your way at this time. And if they don't know what time you're talking about because you have your own solar noon, that's trouble. And it was trouble, and trains crashed. So they had to say like, all right, everybody, let's break up our 360 degrees of longitude, give every slice 1 hour of the day for the 24 hours. And there will be 15 degrees per hour, which is really like the same thing as the rate, right? Every 15 degrees of longitude gets its own time zone. And they tweak it a little bit around cities. You don't want a time zone going right down through like the middle of your city. But roughly 15 degrees per hour. So like if you watch a sporting event that starts on the East Coast, you know what I mean? You're going to watch a Yankees game that starts at that time. But the people in California, what time are they seeing it at? The sun hasn't made it over to them yet. The sun rises first for us here on the East Coast because we're spinning eastward. So they're how many time zones away? All the buses are here. All the buses have arrived. You may be dismissed. You're dismissed. So yeah, that's that. Just do like, and really, I'm probably babbling way too much for what it's going to be. Like each time zone is 15 degrees, and each one of those is an hour. It's earlier in the east. Job done. So let's bang through a couple questions and see how that went. What is Earth's approximate rate of revolution? Now I just took these, and I took them from the most recent like 5 regencies. So that's like maybe 6. So that's 2 years with the regencies. This rate of revolution one was on almost all of them. I couldn't believe it. So that was one of the numbers in the review sheet today that I said, hey, we should stick this in our head. And it is 1 degree per day. We go 360 degrees of longitude in that trip. Every 365 days, it's about a degree a day. When it comes to this question, and there's hopefully is a Foucault one on here that I put. I thought I did. We'll get there. Yeah, it's down there. These sorts of questions are just like, get your points by just sticking to the easy. We know that we spin because of Foucault's pendulum and seasonal constellations. And I don't know if we should write that up here. I'm not going to write it. We know that we orbit because of the seeing different constellations in different spots. So if I didn't just say that wrong, here it is. We know we spin or rotate because of Foucault's pendulum and Coriolis effect. We know we orbit because of seasonal constellations. So star constellations being in different spots, that's going to be because of our orbits. Earth travels in an orbit around the sun. That doesn't happen. That's just straight wrong. That doesn't happen. That's straight wrong. And that does happen, but it's not the right answer. That would go down here with Foucault's pendulum. Foucault's pendulum is the thing that was evidence for our rotation. Cool? All right, 2 questions on circumpolar stars that I kind of stitched together using this diagram. First, this isn't in the question, but remember, if this is the horizon, however high up you got to look at angular-wise, that many degrees, that's your latitude. I didn't find one of those questions for this, but there will be one on the test, I promise. What are they asking us here? The star at the center did not leave because the star is what? It is centered over Earth's axis. As we spin, this is like being on the carousel at the Carousel Mall there. As you're on that, if you could pretend you're on the carousel sitting still and you look up at the ceiling, from your still perspective, the whole ceiling is spinning circles around you, right? It would kind of look like that right there for a partial trip around the center of the carousel. Well, the one right in the middle there would be right above the rotational axis of that carousel. And really, that's what you're on. You're on a big ride here called Earth. So as it spins and you look up, you see the stars whipping around, where really it's you doing the whipping around. Except for that one that's right there, which we call Polaris, the North Star, the pole star. How many days during the year is the sun directly overhead at noon in New York City, or anywhere in New York, or anywhere in the continental United States? The answer is the same, and it is 0. You must be in between the Tropic of Cancer and the Tropic of Capricorn, 23.5 degrees north, 23.5 degrees south. Those are the only places where you will have the sun directly overhead. Outside of that, it's not going to happen. If you were in New York and the sun is coming down directly on top of your head, something is severely wrong with the solar system. It gets pretty high in the summer. Around June, it's going to get up there, but never so that it's coming straight down on you so that you have no shadow. This question is kind of like this question again. If we can see some constellations sometimes during the year, and we can't during other times of the year, why is that? It's because the sun gets in the way. If you're here and my fist is the sun, you're not going to be able to see a constellation that's over there, right? So you'd have to wait until you're over here to be able to see that one. Different parts of our orbits have different constellations. This diagram on Earth at night, you can look off that way and you can see stars. The stars that are on this side of the sun over here, can't see them. The ones that are above us, you can see all year round, like Polaris and the Big Dipper and those guys. But the ones off behind, only during certain seasons. So I'm sure that's what this is asking us. Orion can be observed in winter, but not in the other season. Why? Because of our trip around the sun. Seasonal constellations go with revolution. All right, here's a good one. From September 1 to June 1, the number of daylight hours will do what? So you got to know your dates, right? And we got 12 months and 4 seasons. So divide that out. 12 divided by 4 is 3. Month 3, month 6, month 9, month 12. Those are your 4 special days. 4 special months anyway, right? And they're all pretty close to the 21st. And remember, the regents will allow you to say 21st. If you want to be a little more picky, September 1 tends to be a little closer to the 23rd, then back to the 21st. So that's spring, summer, fall, winter. So what do we got here? From September 1st, right? So somewhere between these, to June 1st, the number of daylight hours will do what? So from September 21st down to December, they're going to be getting shorter and shorter and shorter and shorter until you get to the 21st of December. Right near Christmas is our shortest day. Then they get longer until you get till June 21st. So I'm liking choice 3. High tides, low tides. Again, you could do this if you were like careful and deliberate. You could do this without any of your science prior information, because you could say, Oh no, this one. Yeah, you could. Yeah, you could just say from high tide to high tide. How much time is that? Or you could go to the idea that we've talked about a lot, that they're about 12 and a half hours apart between high tide to high tide. So I'm liking that guy. This is a trickier one, but again, you can do this with the orbit. But what are we looking at? The names and appearances of 4 moon phases in New York State in June or below. What would be June 3rd? So what would be right kind of in here? So it's completely dark, and then by the time we get here, light has come in from the right to a point where it looks like a half moon cookie, but we call those first quarter moons. So that would be the point in between those two. That's really not that bad of a question if you just use it as like follow the steps and figure out the story, what's in between. What do you think? Good enough for that bit of review? There will be more work for you, but if you fought through that and did okay on those questions, that's good news. Test is coming tomorrow, like it or not. And we'll see you then. Be good for the sub.